All right, welcome back, everyone. So our next talk, second talk of the day, will be Stephen Griffeth at Universidad de Talca. He will be talking about subspace arrangements and submodules of the polynomial representation of the rational Cherednik algebra.
Well, thanks very much to all the organizers for the opportunity to speak here. Right, so what Susanna, what Monica said that I would perhaps say something about this paper with Susanna Fischl and Elizabeth Monsalva. Unfortunately, I won't. It's kind of the other, it's closely related to what I'm going to talk about, but I'm not going to say anything about that today. Right, so I hope that the timing's a bit tricky. I hope that I managed to get the timing right. Now I can't. Okay, there we go. I can navigate. All right, so the talk has only two parts. First, a bit about Cherednik algebras. Monica has already done some of my work for me here. And then a bit about subspace arrangements and the connection to the representation theory of Cherednik algebras. So I start with just a finite dimensional complex vector space, which I'll write like it's a Cartan of some Lie algebra, and W, a finite group of linear transformations, which I'll write as if it were a Weil group. But I really want to think about the case in which W is potentially complex reflection group. So I'll use the notation capital R for the set of reflections in this group. These are just the elements that fix some codimension, whose fixed space is exactly codimension 1. And the group is called a reflection group if it's generated by R. And I'm going to assume that for the rest of the talk. I think the way in which I use it is just that the stabilizer group of a point in H is determined by the set of reflecting hyperplanes that contain it. Anyway, so I'm going to write this script A for the set of reflecting hyperplanes for the group, and H circle for the complement and H of the set of reflecting hyperplanes. Okay, so here's the central definition, Dunkel operators. So for every reflection, we can fix some linear form on H whose zero set is precisely the fixed space of the reflection. Of course, there's some freedom here up to non-zero scalars, but which won't matter at all. So I'm also going to fix a collection of complex numbers, which are indexed by the reflections of the group, and which have the property that they're constant on conjugacy classes. And there's also this sort of reality property, which is not really crucial. It's convenient for many purposes, especially if you want to talk about the contravariant form, which I actually won't need to in this talk. However, later I will talk about positive parameters, and the positivity is with respect to this real structure. So given a vector in H, we can define a Dunkel operator, which is its leading term is a partial derivative, and then you have to subtract off the sum over all the reflections weighted by these parameters C sub R. And you can see from this formula that the choice of alpha R is irrelevant because it appears both as a numerator and a denominator. So it's not a real choice. Anyway, so these are certain elements, these are certain differential operators. Well, they're elements of the algebra generated by differential operators on this hyperplane complement, H circ, with polynomial coefficients or rational function coefficients. Semi-direct product, the group W. And Dunkel's fundamental observation is that these operators commute with one another. He observed that really for real reflection groups. His proof depended on the fact that he was working with a real reflection group, but it was later extended in joint work with Optum to all complex reflection groups. Okay, so now I'm giving a somewhat different definition from Monica. Monica defined the Cherednik algebra via presentation, and I'm defining it as a certain subalgebra of this algebra of differential operators. So by definition for me, the rational Cherednik algebra is the subalgebra of this algebra of differential operators, semi-direct W, generated by the polynomial functions on H, the group W, and for each vector V, a Dunkel operator. And since the Dunkel operators commute, they give a map from the ring of polynomial functions on H star into the rational Cherednik algebra. And the PBW theorem says that that map, together with multiplication, defines an isomorphism of vector spaces. So there's a kind of a triangular decomposition for this Cherednik algebra. And of course, this is the starting point of study of category O, analogous to what happens for a developing algebra with a semi-simple Lie algebra. But I'm actually not going to talk about that at all today. I'm just going to talk about the defining representation, the polynomial representation, this ring of polynomial functions on which the Cherednik algebra acts by this construction. So just to emphasize this, I want to go back to so first, the Cherednik algebra is generated by the ring of polynomial functions in the group W. Those both obviously act on the ring of polynomial functions, the first by multiplication, and the second because it acts on H. And the Dunkel operators, well, a priori, I mean, they're elements of this ring of differential operators on H circ. They might introduce denominators. But if you look at the formula, if you act by a Dunkel operator on a polynomial function, it's still polynomial because when you act by 1 minus r acting on a function f is always going to be 0 in the fixed space of R, and therefore it's divisible by this linear form alpha r that we fixed. So the Dunkel operators also preserve the space of polynomial functions. And therefore the Cherednik algebra acts by this construction on the ring of polynomial functions, which I'm writing as this C of H. Okay. So anytime you have an algebra depending on a parameter, of course, you want to obtain information about the way in which the structure of that algebra depends on the parameter. And one of the simplest questions you might ask is, what is the set of parameters C, so that the HC module C of A, this polynomial ring, when is it simple? When is the polynomial representation simple as a function of C? And for real reflection groups, this was answered by Dunkel, du, and Optum many years ago, like maybe almost 30 years ago now. No, wait, can't have been the, yeah, the late 90s, I guess. Anyway, so 25 years ago now. And with Daniel Juteau, we gave an answer for the general case of a complex reflection group. For real reflection groups, the answer was originally phrased essentially in terms of what's known as the multivariable Poincare polynomial. So that's the length generating function for the set of simple reflections, but where you distinguish between the conjugacy classes, if there are. So it's a multivariable length generating function. For general reflection groups, as is probably well known by many of you, for general complex reflection groups, there is no really nice uniform theory of words. And so the Poincare polynomial, well, I mean, of course you can make definitions, but none of them turn out to be extremely well behaved. And the answer is better phrased in terms of what's called a principal Schur element for the group. It's a different Q analog, multivariable Q analog of the order of the group. So the Poincare polynomial, of course, if you specialize it, all the variables to be 1, it gives you just the order of W. The principal Schur element has the same property. It's a different Q analog of the order of W. And it's the zeros of that have something to do with the structure of this polynomial representation, but not all the zeros. So that thing you could think of as a function of C in a certain way by essentially by letting Q be e to the 2 pi I z C. And so the zeros of that as a function of C control together with this positivity property I mentioned earlier, control the simplicity of the polynomial representation. Okay, so sorry, I just realized I don't know exactly. I have until what time exactly?
12:20 and 5 minutes per question.
Okay, so I'll stop at 12:20. Okay, perfect. Yeah, so right, so the zeros of that principal Schur element correspond, well, shall I say positive, the zeros of that which lie on positive hyperplanes in the parameter space determine those are the points where the polynomial representation is not simple. So it's some explicit family of hyperplanes in the parameter space. Okay, so we'll call a parameter singular when the polynomial representation is not simple as an HC module. And I'll write sing sub WC for the set, given any parameter, I'll write sang sub WC for the set of all polynomials which are annihilated by all Dunkel operators. These are often called singular polynomials. Since the polynomial representation is simple, exactly if there is no non-constant singular polynomial, Dunkel, du, and Optum pose the problem of determining the set of singular polynomials. It's been solved for some classes of groups. I think for dihedral groups, it's known, although I forget, maybe Dunkel, du, and Optum actually worked it out for dihedral groups. And Dunkel solved it for the symmetric group. So in any case, for dihedral groups, I suppose that Chmatova's work determines this set as well, even if Dunkel, du, and Optum didn't do it. Anyway, right, so Dunkel determined all the singular polynomials for all values of the parameter, all possible values of the parameter when W is a symmetric group. And just like in Monica's talk, the parameter is singular exactly if it's a positive rational number with denominator somewhere between 2 and n, where n is the n of the symmetric group. So in Monica's talk, you might think of that denominator n as being, in some sense, the least complicated of the interesting possible denominators for the parameter. Okay, so this space of singular polynomials is, by construction, well, but because of the homogeneity of the Dunkel operators, it's a graded W module. And so if you want to give some description of it in an efficient way, you should describe its graded character. So you don't have to write down like a vector space basis, which would be more complicated. Its graded character as a module for the group W. And that's essentially what Dunkel did. Although he actually did do more than that. He gave a basis, a specific set of non-symmetric Jack polynomials. And part of the subtlety here in this work is that he had to pen down exactly these Jack polynomials. They're polynomials whose coefficients depend on this parameter C. And part of the subtlety was in his work is that it's not clear when they have poles and when they don't. So he was of course interested in C for which many Jack polynomials do have poles, and there it's a relatively difficult problem to say exactly when a particular non-symmetric Jack polynomial has a pole at that parameter value or not. So a lot of his work went into giving sufficient conditions for a specific Jack polynomial not to have a pole at a specific parameter. Okay. So the existence of singular polynomials, as we already saw, is closely related to the existence of non-trivial submodules in the polynomial representation. And there's actually a correspondence. It's not a bijection, but if you start with a submodule of the polynomial representation, then its lowest degree subspace is actually a graded W submodule of the space of singular polynomials, which is irreducible as a W module, provided that your original Cherednik algebra submodule is not a sum of two proper submodules. If there's no non-trivial way to write it as a sum. And conversely, if you have a irreducible graded W submodule of the space of singular polynomials, then the ideal it generates is a Cherednik algebra submodule of the polynomial ring. So, right, and I just mentioned it. This doesn't give you a bijection between these irreducible graded subspaces of the space of singular polynomials and submodules. The point is that not every submodule is generated by its lowest degree space, and not even by the singular polynomials it contains. And the example that I always like to keep in mind is it occurs already for the Weyl group of type B2 for a certain choice of parameters. Anyway, you should think of it as sort of the typical behavior that submodules are not generated by the singular polynomials they contain. However, you still thinking about the problem this way does give a possible strategy towards solving this problem that Dunkel, du, and Optum posed of classifying the singular polynomials. First, classify all submodules, and then for each submodule, determine the space of lowest degree, which will be one of these spaces of singular polynomials. And that will give you all irreducible homogeneous subspaces of the space of singular polynomials. All right. So in the symmetric group case, this unfortunate thing that happens that I mentioned happens for the Weyl group of type B2 actually doesn't happen ever for the symmetric groups. So that follows from theorem of Eddinghoff and Stoica, which classifies all the submodules of the polynomial representation in the case of the symmetric group. And I should mention there was previous work. Eddinghoff and Stoica, in fact, the only new thing they did, I guess their result was only new when the denominator of C was exactly 2. I should have mentioned that here, but now I forget the name of the person who did this, who had already done this for denominator larger. I guess Enomoto. Anyway, so I apologize for that. I should have mentioned it here. Anyway, so what is the structure of the polynomial representation in the symmetric group case? It's always uniserial. In other words, it has a unique composition series. All submodules form a nested chain. And every submodule is generated by its lowest degree weight space, which is a certain irreducible space of singular polynomials, which Dunkel had previously classified. So in other words, historically, what happened in the symmetric group case is at first Dunkel classified singular polynomials, and then using that, other people were able to finish the classification of the submodule structure. I sort of suspect, though, so there is an easier proof in the symmetric group case, which goes the other way around. And I sort of suspect that in general, if somebody wants to try to work on this problem, it's easier to first classify submodules and then classify their lowest weight spaces. Anyway, so which submodules arise? Well, they're all ideals, obviously, being Cherednik algebra submodules, they have to be ideals in C of H. And so you might ask, what are their zero sets? And their zero sets turn out to be subspace arrangements in Cn, some interesting subspace arrangements, the ones where you have some number of blocks of k coordinates, and within each block, those k coordinates are equal to one another. So in particular, the k, what's sometimes called the k equals arrangement, arises this way as the socle. The ideal of the k equals arrangement is the socle of the polynomial representation when the parameter c is 1 over k. It's one example of one of these. Right. So if you hope to apply techniques from representation theory to study the ideals of these subspace arrangements, then the first question is just which subspace arrangements arise from submodules. And we have a partial answer. We know when the radical of the polynomial representation is a radical ideal, and we know when the socle of the polynomial representation is a radical ideal. So those are the cases, the sort of most obvious cases in which representation theory might be used to study these subspace arrangements, because in those cases, we actually have some irreducible representation of the Cherednik algebra, which is equal to either to one of these ideals, to the ideal of a subspace arrangement, or to the coordinate ring of a subspace arrangement. And for the rest of this talk for today, I'm only going to talk about what happens with the radical of the polynomial representation. So maybe I should pause for a second and ask if there's questions so far. All right.
So actually, there were a couple of questions in the chat that went unanswered.
Oh, sorry, I can't see the chat actually. Let me just get it up.
No worries.
Okay, sorry, I didn't have it open and I didn't see it on my screen.
No,
so,
we should have read them out. No worries.
Okay, yeah. So Ben asked about what is the principal Schur element. Okay, yeah. So these are written down in the paper with Danielle, my only joint paper with Danielle Juteau. But let me just say what it is for the symmetric group case. I guess there it's the same as the Poincare polynomial. It's the Q analog of n factorial. And for the group G, M, M, N, it's very similar. It's basically the Q analog of n factorial, also for those groups. And then Matt asked, are Jack polynomials characters of some RCA modules? No. So no, right. So McDonald polynomials are characters of irreducible RCA modules at parameter t equals 0, like from Monica's talk, which is somehow the case orthogonal to what I'm talking about. So if I just go back to the definition here, my definition of Dunkel operators has t equals 1. It's the coefficient of this partial derivative that appears in the definition of Dunkel operators. So if you completely turn off the partial derivatives, then you get the situation in which McDonald polynomials arise as characters. Jack polynomials in this context play a completely different role. They're elements of representations. They're eigenfunctions for these U operators that Monica mentioned. That's the role they play. So they're exactly the basis that Monica was talking about. However, as Monica mentioned, you don't always have diagonalizable modules. In fact, many of the most interesting representations are not diagonalizable with respect to that Dunkel-Optum algebra. And that was what has to do with this fact that I mentioned, that most of Dunkel's work, not most, a lot of Dunkel's work had to do with pinning down when certain eigenfunctions actually existed, when they didn't have poles. Okay. Okay, and then Ben asked, in type A, this collection of ideals seems like the ideals generated by spect modules. No. So if you take the socle is always generated by the Garnier polynomials, which I think we've discussed before, Ben. But that's the only one, basically. So all of the others occur at higher degree than the Garnier polynomials. The Garnier polynomials, I think, at least if I understand your question correctly, by spect module in this context, you mean the submodule of the polynomial representation, which occurs in lowest degree. Which is the lowest degree occurrence of its isotype. Is that right? In that case, the answer is basically no. Right. Yeah. Okay. Well, anyway, let me know if I'm wrong about that. It's essentially, but I think the correct answer to your question is basically only the socle is generated by that lowest degree occurrence of its isotype. The others are more complicated. Okay. So anyway, I want to focus. So the socle in many cases is more tractable than the radical, largely because it tends to want to be a unitary representation of the Cherednik algebra, and so we have more tools to study it for that reason. The radical, its top. Well, I'll say what we can say about it, but somewhat less. Except at least in the case of the symmetric group, where I guess work of Jose and Norton and Chris Bowman, I think they were able to give essentially a formula for its Kajan-Lustig character by relating it to the socle. That's my understanding. Okay. So we can stratify H by stabilizers. So the action of the group W induces a natural stratification. You just say 2 points in H are equivalent if they have the same stabilizer, the same parabolic subgroup stabilizes them. I'll call the equivalence classes strata. And for a reflection group W, 2 points are in the same strata exactly if the set of reflecting hyperplanes that contain them is the same. Right, so I just mentioned this. Any subgroup which is the stabilizer of a point in H is called a parabolic subgroup. So this stratification is determined by the lattice of intersections of the hyperplane arrangement of reflecting hyperplanes. And given an intersection of some set of elements of A, I'll just write W dot F, given an intersection F, a flat. I'll write W dot F for the unit of its images by the W action. And so there's a bijection between subsets of this type of H and conjugacy classes of parabolic subgroups W. Oh, okay. Thanks. Jose clarified in the comments exactly what they did. Great, thanks. When the parameter divides the rank of the symmetric group, right? Yeah, which is often a slightly easier case than the general case. Although probably, well, anyway, okay. So the top of this polynomial ring, that is, so the top by definition just means a quotient by the radical. It turns out to be simple. That's true for all objects of category O, and in particular for this polynomial representation. The representation theory allows us to say some things about this just a priori. So there's this following theorem. For positive parameters C, the CH module L is Cohen-Macaulay. This theorem, the proof is actually quite easy given previous work. So it's essentially just a combination of an observation of Eddinghoff, Gorski, and Losef that any minimally supported object of category O is Cohen-Macaulay, together with the work that I did with Danielle, computing supports of L. So as it turns out, for positive parameter C, the top of the polynomial representation is always a minimally supported object in its block, category O, and that combined with a slight modification. I mean, basically the same proof of Eddinghoff, Gorski, Losef's theorem works in that context. So I haven't defined precisely what I mean by positive. I'm not going to, but it's a certain full dimensional cone in the parameter space, and the significance is that the polynomial representation is actually a projective object in category O when the parameters are positive. Okay, so it's possible to classify parameters for which L is the coordinate ring of a subspace arrangement. In other words, parameters for which the radical of the polynomial representation is a radical ideal. I'm not going to describe that classification. It's pretty involved. But I'll say what it says for these monomial groups G, L1n, which include the symmetric group and the Weyl groups of type B. And of course, many other complex reflection groups. I'm also not defining these monomial groups. I hope that people know what they are. Maybe I'll say, this is all n by n matrices whose entries are either 0 or else roots of 1. And so that the non-zero entries, there's always a unique non-zero entry in each row and each column. So they're Reith products of cyclic groups by the symmetric group, in other words. Okay, so there's a kind of a bunch of data here. You fix positive integers n, l, and k with certain properties, and also an integer m between 0 and n. And let p be the greatest integer at most n minus m over k. And then there's a certain set of points z, l, m, and k, z, l, m, k, which is all points satisfying some coincidences between their coordinates. So some of the coordinates should be 0. Some of the L powers of the coordinates should be equal to one another. It's some generalization of the k equals set or things like it to allow L powers and some zeros. And then if you just take this previous result that I mentioned and translate it into the language of commutative algebra and this variety, this homogeneous variety in Cn, then the result says precisely that this variety is Cohen-Macaulay. So when L is 1, this is exactly the result of one of the results of Eddinghoff, Gorski, and Losef. It's interesting. I mean, I don't think there's a nice way to obtain. At least I don't know an elementary way to obtain this using sort of combinatorial commutative algebra. It seems to be a difficult result to get without representation theory. The proof I should have mentioned, the proof of Eddinghoff, Gorski, and Losef's result is well, one of the proofs relies on Ringel duality for Cherednik algebras. That's more or less the main ingredient. Okay. So you can prove some things that are relatively difficult without representation theory. Seem to be difficult to prove by using this identification of coordinate rings of subspace arrangements with representations. All right, so now I want to say a bit about what we know about the submodule structure of the polynomial representation in the case of these monomial groups. It's quite a bit more complicated than the symmetric group case, but conjecturally not unmanageably so. So in this case, the parameter is not just one number, but well, it's really an R tuple of numbers. I wrote here an R plus 1 tuple, but there's a certain normalization, which means it's actually an R tuple. So first of all, if this parameter C0 is a rational number with denominator somewhere between 2 and n, then there's a chain of submodules which comes from the ones in the Sn case in a certain explicit fashion. So these guys are the ones whose the zero set of one of these is like the set of points in an n space where there are some number of blocks of k coordinates whose lth powers are equal to one another. That's the flavor of the flavor of the associated subvarieties. And then, so that's how you can get submodules if this parameter C0 is specialized. And then there's other types of equations that might hold between the parameters. So if I have an equation of this type, which depends on these integers p and q, then I get a submodule ZPQ, whose associated subvarieties has some number of zeros. Q zeros, I get Q plus 1 zeros, I guess. And then there's there's a conjecture, my conjecture, the EZ submodule conjecture, which is that the lattice of submodules of the polynomial representation is generated by these two types. And in particular, it would give an explicit description of the top of the polynomial representation of this irreducible module L for all parameters. So I don't say it here, but all of the submodules that appear in this conjecture have quite explicit generators, certain Jack polynomials. And so it really does give some kind of a description in particular of the radical of the polynomial representation. Just take the sum of all the submodules that appear. That's interesting, at least to me, because it's not trivial in general to compute the character of this representation L. Okay, so there's a little bit of evidence. At least it predicts the correct support. In other words, it predicts the correct zero set for the radical of the polynomial representation. And it's true if you demand that some parameters be generic. And then my hope is that the behavior of the submodule structure is determined for arbitrary parameters from what happens in codimension 1. On the other hand, it is a little bit weird. It's quite a strong property for the lattice of submodules of a standard object of O to be finite. That's not typically the case. So there should be something going on for the polynomial representation if it's true. Why should its submodule lattice be finite? It would be nice if there was some structural reason for that to happen just for general groups W, but I don't know what I believe in for other W other than monomial groups. I'm not sure. I'm not sure what's true. Okay, so that's it. Thanks very much. I'm done.
Awesome. Thank you, Stephen. Do we have, we have about 5 minutes for questions and then take a short break before the next talk. Does anyone have any questions for Stephen?
Yeah, hi. So this L representation that you have, the simple equation of delta 3, you say that it's always Cohen-Macaulay, at least for this positive parameter. Do you know when does it have minimal support?
Always for positive parameter. That's the point.
Always?
It's always minimal support in its block. I didn't say so. So this is perhaps a slight distinction with the original theorem of Eddinghoff, Gorski, and Losef. What I use is the theorem that any minimally supported in its block object of O is Cohen-Macaulay, which follows by the same proof.
I see.
And so, right, so this thing is always minimally supported in its block for positive parameters. That's the role positivity plays in this context.
So it will never be in the same block then as some finite dimensional representation, for example. It's either finite dimensional or it's not in the same block.
Unless it's finite dimensional.
Okay, thank you.
Yeah, of course, it often happens that L is finite dimensional and there's lots of other finite dimensionals in that same block. That does tend to occur.
Thank you.
Ben says he has to run, but
What?
Ben Elias says he had to run early. He had to leave early.
Oh, okay.
Well, if there are no more talks for Stephen, maybe we can take our break starting now and then resume in 10 minutes for our next talk.